All right. So we're talking about lab one, and we've been working on, we've had this spreadsheet, and um, up till now, I've had these 3 videos on the main spreadsheet. I mean, the main playlist. There they are. This is just an intro. It's longish, and I just haven't had a chance to chop it up. And there's older ones here. And so I made, because I wanted to make your lives easier, though, I made these 3 real quick. And even they could have been a little better because cleaned up spreadsheet. So in principle, you've been through these 3. And now you have something that looks like this. Not this one, but you have your 3 blocks for ruler, caliper, micrometer. Well, of course, there's a 4th one for the scale. And then you have your summary table right here where we said we concatenated everything. And also we've been through these error propagation equations. So as I've done previously, we created these 3 blocks here to sort of say, how can we draw some conclusions? And similarly to what we've done in the past, I did this discrepancy value, which is just the difference between the accepted value and your measured value. But I haven't multiplied by 100. I just wanted to know what is the actual discrepancy in the difference in the number, in the units of the measurement. So that is the difference between my measurement and an accepted value. And now we also have the error bar on our value, on our measurement, or our final plus minus. And I made the relative uncertainty, but it doesn't look like it matters. And now what I'm doing is I'm looking at the difference between my error bar, my plus minus density, and the discrepancy. And I'm calling that my figure of merit. We've done that before. And what we want to see is we want to see a positive number. And the way I have this set up, and it may be a little confusing, but I made a nice little graphic graph that is much easier to understand. Human beings process graphical data much better than table data. But what I want to see is that even if I don't quite get the right number of the density, I want to see that my error bar is bigger than the difference. And if the error bar is bigger than the difference, I'll get a positive number. And it will and also, first of all, the smallest one of these discrepancies is going to be basically my material, because we all had different materials and we want to see what they are. And so I can right off the bat say, look, this is the smallest discrepancy, so I must have brass. But I also want to know that my error bar is bigger than the difference, because if my error bar is bigger than the difference, then everything is cool. If not, then that means that my measurement might be kind of cool, but it's, you really can't claim that you got the right you ended up determining what the material is. And so we pretty much have decided it's brass. And I'll go over how to make this table, but I want to connect together the figure of merit. Now, you guys, remember, one of our colleagues was nice enough to throw this data up quickly, and we kind of feel like that person made some mistakes, and I'm sure that they fixed things up. But in any event, you'll notice that each time the smallest discrepancy is for brass. So that's good. But you also notice that our figure of merits are all negative. And so if we look, we can see, number one, these lines represent the measurements with the three different instruments. And the blue dots represent each of the accepted densities. So in principle, all three of them should have been, these three lines should have sat on top of each other in the ideal world, and each one of them would have had a smaller and smaller error bar. Now, in our case, somehow the more precise instruments didn't get it right, only the ruler got it right. So because our error bar is smaller than the difference, what we would say to people if we wrote a report that, yeah, I produced a very small error bar, which is my, this is my precision, but my accuracy, so make sure you write the word down, my accuracy is off. And accuracy is how close I am to the real value. So I have very precise measurements with the calipers and the micrometer in this set of data. I don't know what your data looks like. So I'm giving you the tools to describe your data. So in my case, I produced a very precise measurements, but with the calipers and the micrometer, my accuracy is off. Now, remember too, in real research, we wouldn't know the right number. So part of this would be we'd be comparing to other people's measurements, and we discuss their techniques, and maybe they have some systematic errors and all that. But that's kind of beyond physics 1100. I just want to show the purpose of this lab is to show you how to propagate your error, and within the scope of what we have here, how can we interpret? So in the case of the ruler, if all we used was a ruler, we could declare victory. We didn't get quite the right number, but our error bar is large enough so that we know that we can claim that we found that it's brass. And a really nice setup would be if two densities were very close together. And notice that carbon steel and stainless steel are very close together. And it looks like that if I only used a ruler, I wouldn't be able to tell the difference between carbon steel and the stainless steel, because if I had my line down here, it looks like the error bars would still be so big that both dots would be within the error bars. So it would be necessary to use the calipers or the micrometer to be able to tell the difference between those two. So I've kind of gone to the end and shown you this graph, and I'll go back to the mechanics of the graph in a minute. Another takeaway from this lab is that you should notice that the error bar on the micrometer is smaller than the calipers and smaller than the ruler, but it's not that much smaller. And one thing I could do too, let's take a look at the volume. First we got the volumes, right? And you look at the plus minuses of the volume, and you're saying, well, wait a minute though. The plus minus on the volume for the micrometer is 20 times better. But my density, the difference between the two density plus minuses is not that much different. It's not 20 times better. Why not? Because what happens is we have the micrometer or the calipers are very sensitive instruments, but we still used the scale, and the scale isn't that great. And we could go back to the relative error on the mass. And I don't know if I quoted that, but maybe I did. Let's take a look over here. plus minus mass. Okay, we didn't do a relative mass, but we would see that it's not too great compared to the other ones. But if nothing else, right away, 0.06 is nothing like point, that, look at that. That's 0.0006. That's now 100 times better, right? But when you add things in quadrature, mathematically speaking, so there's our this is the volume, and now we're doing it with the mass. We're adding the relative errors, squaring them and square rooting. That's adding in quadrature. The bigger one always dominates. So one of the takeaways here is that it could be that if we are stuck with a certain scale, it may not be worth it because it took a lot more time, right, to measure with the micrometer. And maybe in your professional lives, the Offenbach 200 isn't good enough. So you tell your boss, we need the Offenbach 4000 to make better measurements, and you have to prove to the boss that it's worth it. And if the Offenbach 200 versus the Offenbach 4000 both depend on scale 1 from back in the Stone Age, then your boss is going to get mad at you if you spend all the money for the Offenbach 4000 but you don't get a very much of an improvement over the density measurement because you were stuck with the archaic scale. So that's one of the takeaways here is that, yeah, I get a better plus minus volume, but do I get a better plus minus density? And the short answer is yes, but is it that much better? So our takeaways are about discrepancy and size of the error bar, and is it worth it to go to the more sensitive measuring device? And of course, basically learning how to propagate the error. So do you have any questions about that part, the basic, basic conclusions and takeaways? Would anybody like me to repeat any of that? Good. And of course, I'll post this recording. So we need to get into the mechanics of how did I create this. So what I did is I made yet another table. And this part was pretty easy because I simply well, be careful what I need in grams per millimeter cubed. So what I did is I'll show you a little trick. You do copy, and in this case, it's not that big of a deal, but do paste values. And the same thing here. Whoops. And I copy, and I pasted values because it complained to me. And then stuff like I want to format that, so I center it, and I want to wrap text so it all fits in. Now, to make my life easier down the road, I decided to get rid of this row. And here, I just realized I needed to also add the units, grams per millimeter cubed. Okay. So there you notice that we've been using scientific notation, so I formatted it. And all right, so let's go on. So you notice now I have the ruler, the plus minus rule, the plus minus ruler density, the caliper's density, et cetera, et cetera. Now, here is the little trick, and you're getting to learn more about the power of spreadsheets. Here is the measurement of mine. And it's very similar to here. I mean, in principle, okay, here's, if you wanted to, I just realized we can do this a different way. You could just simply select these because I've already done them. In principle, you've already done them, right? Copy. And I can just do, I'm going to do paste values because I just want, well, there's two ways to go about this. You could paste, and what you'll see now, it's an address, see? And you might want to do that because that way, if one of these changes, it goes immediately down here. And I think I goofed a little bit there. Oh, plus minus, I got it right. So density, I select these and I copy and I paste. Yeah, I think that's better. And just to show you, well, what I did originally was I put here equals, and I went up here, and then I hit the F4 key, and then I hit enter. And I went across and did this for each one of them. Now notice now I've got from the calipers, and same thing here. And now for the micrometer, and I put the dollar signs in. And now, and then let's say we've been doing it that way. So now I can select all of them and drag the fill handle down. And it's always referencing the same place. That's one way to do it. And the other way to do it is just to simply copy and paste. And that works nicely because it's the same number of rows up here, but we made it that way, right? So as you use spreadsheets more and more, you get to learn how to anticipate. Oh yeah, I don't have, well, you guys, I'm pausing just so you guys can catch your breaths. Of course, with the recording, you can always stop and restart. Now, how are we doing time-wise? Oh, we got about 10 more minutes. Okay. No, less than, we have to be done in 6 minutes. We have 6 minutes. Okay, so let me get, first of all, just look at this. So for me, this is an A plot. I got title, I got fancy with formatting, and I have a legend, and and in fact, I probably have to stop and restart, and I'll record how to do all this stuff, but just so you see it. Okay, so and I created this like while you guys were working, you may have noticed I made a lot of mistakes and I redid it. So let's see if I have an idea that I want to see if I can do this in less steps. So watch what I do. So I'm going to select that. Oh, I can do this actually. But now I want to get the calipers and the micrometer. So I hold down the control key. Oops, went too far. Hold down the control key. All right, so I'm hoping. So control key is when you want to do here's a big word, non-contiguous selection. Contiguous just means next to each other, like the 48 contiguous states plus Hawaii and Alaska. And I'm going to insert, and now we're going to insert what's called a line chart because we can't get text labels in a scatter plot. And this is pretty cool. I just learned how to do this. I've been puzzling about how to make this graph to compare a variety of measurements. Now I've done it in other ways, but I didn't know how to produce the other ways. So now what we do is if let's make believe we're a Mac user too, Mac Windows. So we need to format our data series, and it's sort of the reverse of what we've done in the past. So density accepted, we don't want to have a line, and we do want a marker. And notice I'm selecting built-in instead of automatic because I can change the size. And I thought there was a round one available. It's round. So now you see those are the accepted values, so we keep them that way. And you can, in principle, there we go. And now I do want the line, but I want to make it really thin. And I do want a marker. And I want to make them quite small, though, because if I don't, you'll see later on that the error bars can't be seen. I'm going to go a little quickly because, again, you guys can go to the recording. And let's see, marker, built in, pink, fine, just make it smaller. And also here, make the line solid line, make it smaller. And then marker. And built in, and I want it small. Okay, now, there it is. Notice it's not quite the same because what I did here is I zoomed in, but I'll show you how to do that. You know, maybe it's going to happen later. And now I learned another trick to save some pain. Now, when I insert error bars, I make sure I have I selected one of the series. Because if I just say insert error bars, it puts it on the known ones too, and we don't want that. Error bars, and then I select the other series. Error bars, then the last series, error bars. What's the time? It's time to go. Okay, so I'm going to have to make another video to finish this. Let me save my work here, and I'll get on that. I'm done at 6 o'clock. So I'll either do that this evening or I'll have to wait, or I'll get on it tomorrow morning. Okay, so any quick questions? Because we all have to move on to our next